Hello and welcome. In this worked example video, we'll be looking at the energy dissipated by frictional forces, as the title suggests. The question reads, a car of mass 500 kilograms is at rest at point X on a slope as shown. The car's brakes are released and the car rolls down the slope with its engine switched off. At point Y, the car has moved through a vertical height of 30 meters and has a speed of 11 meters per second. What is the energy dissipated by frictional forces when the car moves from X to Y? Let's think about some key language and the clues that are provided in the initial information. If they give you the mass, then we can assume, okay, this is here on Earth. This person isn't wearing a spacesuit, and so we could calculate the weight of this thing. So maybe that's important, calculate the weight. So if we just kind of read through it, we know that this car has mass. To say it has mass means it has weight equal to mg, and we know that g is 9.81 newtons per kilogram. And so one of the things that we could do without even sort of going any further than that is just say, well, how much weight does this thing have? Maybe that would be important to know. 500 kilograms times 9.81 newtons per kilogram is a certain amount of weight. Okay, so we could get that. And remember, weight acts straight down. There's a component of this weight which is acting into the ramp, and there's a component of the weight that's acting down the ramp. It is that component of weight that allows this car to just sort of roll down the slope, right? A component of weight acting this way means there's going to be a net force that way. There's not enough friction to stop it, but there is some friction because we're solving for the energy dissipated by the frictional forces. When they tell us the car has moved through a vertical height, but they don't tell us the actual distance traveled here, it's saying we should use potential energy due to gravity. Potential energy due to gravity is equal to mgh. And so the mg, the weight of the vehicle, we already kind of talked about, okay, we could calculate that. But what we really want to calculate is how much potential energy will the car possess 30 meters above this sort of arbitrary zero. We know something about the speed of the car at that point. And my intuition tells me that if we were to calculate the potential energy and say, if there were no frictional forces, all of the potential energy would show up as kinetic energy. And we could say that all the mgh that this car possesses up here, all of its potential energy due to gravity, could show up as energy of motion 1/2 mv squared. And we could solve for what that velocity would be. In fact, it doesn't really even matter that this thing is 500 kilograms. We could solve for the velocity as just root 2gh, right? So double both sides, take the square root of both sides, and the velocity should just be the square root of 2 times 9.81 times 30. Now, when we solve for this velocity, I can almost guarantee you it's not going to be 11, but it's going to be higher than 11. Because, again, this is saying there's no energy lost. All of the potential energy gets converted to kinetic. And that's not the case because they're telling us what the speed is. And then they're saying, it's kind of like this. The question would be friendlier, is sort of friendlier wording if it said, if the speed is only 11 meters per second, then how much energy was dissipated by frictional forces? Because it's kind of like suggesting then that, hey, we're missing some speed here. There's an energy sort of budget that we need to account for. That energy is neither created nor destroyed. So if the potential energy this car possesses up here doesn't manifest itself as kinetic energy of motion down here, then there must have been some energy losses due to friction all along the way. And they just want to know what is that sort of value. And so the calculation, I think, really becomes calculate the potential energy, subtract away the kinetic energy that we can calculate from this empirical data. It's kind of like they tell us what the speed is. Somehow we know that this thing is only going 11. I'm sure if we calculated this, and maybe some of you already have, this number is bigger than 11. So we'd say, okay, well, if the speed is only 11, that means that the difference between those energies must be the energy that was dissipated by friction. And it could be friction between the air particles that are here, right? The car is crashing into air, and so that's a frictional force. There's friction between the tires and the road, right? That's a frictional force. So saying just all the frictional forces, we're missing some energy because 1/2 mv squared for this speed is going to be less than the mgh, the potential energy due to gravity up here. All right. So they don't tell us what angle this is. We don't need to really calculate the component of weight going down and multiply it by a distance. That's another way. It's like the work done by friction would be the force times the distance, right? But we don't need to do all that. It just wants the total energy. So the calculation becomes, what is mgh? Subtract away the 1/2 mv squared, and all the missing energy must have been dissipated by friction. All right, so let's work through that sort of over here. We got the potential energy, 500 kilograms times 9.81 newtons per kilogram times 30 meters. That gives us a total potential energy of 147,150 joules. Note that if all of this potential energy did become energy of motion, then the velocity would be this. It would be 2 times 9.81 times 30 square root. So the velocity you get from this that I really want to emphasize now would be like, there is no friction. This is on a frictionless surface. You get actually 24 meters per second. So if you could somehow convert all of the potential energy due to gravity that an object, this mass possesses here into kinetic energy, it would be going 24 meters per second, not 11. The fact that it's only going 11 means, again, we've lost some energy along the way. And so we need to subtract away something that is perfectly calculable, 1/2 mv squared. So we know that we've got a 1/2 500 kilogram object going 11, we square it. So the kinetic energy of this object at this point, because they give us the speed, is calculable, right? So we're just going to subtract away a 1/2 mv squared. So 11 squared is 121. 121 times 500 is 60,500. And then divide that by 2. And so the kinetic energy is only 30,250. And so if you had something with about 150 kilojoules of energy, and then there's only 30 kilojoules of energy sort of left in energy of motion, that means most of the energy was actually lost along the way due to friction, right? How much energy? 147,150 minus 30,250 gives us 116,900 joules, which we could say is like 1.2 by 10 to the 5 joules, right? So round this to 2, because that's bigger than 5, and that agrees with choice B.